So let's take a look. Let's take a look at this first example. On this first example, we've got an equation. On the first side, it's a series of things added up. So we've got 3 plus 6 plus 9 plus, and then we keep on going up to 3n. So the idea is the first value is 3 times 1, which is 3. The next one is 3 times 2 is 6. The next one is 3 times 3 is 9, and the next one would be 3 times 4 is 12, and so on and so forth. We're going to leave that at where it stops at the top at 3n, and then they're saying that whole thing, when you add it up, will always equal 3n times n minus 1 over 2. So we want to show this by what's called mathematical induction. Well, let's do our step 1. Our step 1 always says that what we're going to need to do for step 1 is to look at when n equals 1. So step 1 says plug in n equals 1 and make sure it works. So if we look at the above equation, n equals 1, then if you plug in 1 for n, it means you'll only have the first value, just 3. You'll stop there. You won't keep going. But then you also have to plug in 1 to the other side for all your n's. So you'll have a 1 here and a 1 here for both of your n's on the right-hand side. And that's what we did on the right-hand side. And now we want to make sure these two sides are equal. Well, on the right-hand side, the first thing you'd want to do is what's inside of your parentheses. So you do the 1 plus 1, which is 2. And then what we would want to do is, well, we've got all this multiplication on top of our fraction. We've got a 3 times 1 times 2. Let's go ahead and do that. 3 times 1 times 2 is just 6. And then do the division that's already listed. We've got 6 divided by 2. Does that equal what we have on the other side, the 3? And absolutely it does. Yes, it works. So what does that mean? It means that our first step is complete. We have shown it is true for n equals 1. Now what we're going to do is step 2. Step 2 says, okay, let's assume it's true for some value k. So we'll plug in a k wherever there's an n. So instead of stopping at 3n, we'll stop at 3k. Instead of it being 3n for our first term on the right-hand side, it'll be 3k. And instead of n plus 1, it'll be a k plus 1. And what we're going to do is the mathematical induction says assume that this is true. So we're going to assume that this is fact. So we're going to say, whether we believe it or not, we're going to assume it is true. Now, what are we going to do? We're going to use this little tidbit here, this one that we're assuming is true, to help us prove that it's true for k plus 1. So we need to look at how to find s of k plus 1. So we're going to look at the term that comes after the one we just looked at. Instead of k, we're going to go one past that to k plus 1. So our sum normally starts at 3 and goes up to 3k, but we're going to go one past that. Instead of stopping at 3k, we're actually going to stop at the one after that at 3k plus 1, which means take the k plus 1, the next number, and multiply it times your 3. Now, normally, the next piece on the right-hand side is a k, but we're plugging in k plus 1, so it'll be a k plus 1. And next, we normally have a k plus 1. Well, we're going to replace that k with a k plus 1, and then we'll still have the normal plus 1 that's there. So we're plugging in that k plus 1 for this k here. For that k there. Okay, now, let's see how we can play with both sides and see that both sides really are the same thing. Well, the first thing that I do notice is on the right-hand side, so I'm going to do a little bit of tinkering, is that 1 plus 1 over here on the right-hand side can just be simplified to 2. That's something at least. On the right-hand side, we've got, let's see what we have. We have this 3 plus 6 plus all the way up to 3k. Well, that's what we have that we were assuming was true up top using our k. Well, what it says is that 3 plus 6 all the way up to 3k, that left-hand side, what we've got here, is equal to, whatever's on the right-hand side, is equal to this guy. 3k times k plus 1 over 2. So what we'll do is we'll make the swap. We'll replace what we have here with what we had on the right-hand side over here. So we'll replace it with the 3k times k plus 1 over 2. So all we did was make a swap using what we said was true. So we just made a swap of these two using our special little start equation that we were assuming is true. Okay, so again, the goal is to kind of force the left hand and right hand sides to kind of play with them and make them look the same. Well, notice what I have here is I have a fraction on the right hand side here, but I've got two pieces on the left-hand side, one of which is not a fraction. So what I want to do is make these both fractions. Well, this one already is. So how do I get the second piece over here to turn into a fraction? Well, I need to get a common denominator. Currently, it has a 1 on the bottom. So how do I get a common denominator? Well, I'm going to do what we do here, which is I'm going to multiply the top and the bottom by 2 to get a common denominator. Well, notice that's what I did here, multiplied the top and the bottom by 2. Well, notice if you multiply that top by 2, we've got a 2 times a 3, which will give us a 6. On the bottom, you'll end up with this new 2. That's okay. Be careful, do not reduce the 2 into the 6 or else you will lose your common denominator you just got on purpose. Now, we do have a common denominator in LCD, so we can combine these because they both have a 2 on the denominator. So we can combine them as a denominator of 2. On top, we had a 3k plus 1. And we had a 6 times k plus 1. So now they're just on top of the same fraction. Now, what can we do next? Again, we're getting closer and closer to the left and the right looking the same. They're just not quite there. Well, if we continue along in the same fashion, what we'll notice is that both of the terms on the top have a 3 and a 6. So they have a greatest common factor. We can factor out a 3 from both of those. So if we factor out the 3, and what else do they have? They also have a k plus 1. So let's factor out the 3 and the k plus 1. Well, on the first piece, if you factor out the 3 and the k plus 1, you're still going to have the k there. So that'll be part of your leftovers. However, if you factor out a 3 from the 6, you'll be left with a 2. That's why we have a 2 down here. But the k plus 1 will vanish. So our leftovers, the k and the 2, will be inside of their own set of parentheses. Well, notice now what we have is, notice if we compare the left and the right-hand sides, now they are identical. This is what we were looking for. Now we've proved using the k term, assuming that the k term was true, we have now proven that it would also be true for the next term, the k plus 1 term. And that's all you need to do for mathematical induction. For your second step, we already did the first step, which was proving it worked out if n equals 1. So we've done the hard part now. Both sides are equal, and this statement is true for any n. That's what mathematical induction does for us. Now, we kind of tinkered with both sides of the equation until we got both sides were the same. You could have tinkered with your equation in a different manner. I did it one way, you could have done it in another. As long as you get to the same point where both sides are the same, you're technically proving the same thing. So you might just choose to do it a little differently, and that's okay.